It's a pleasure to be here. I'm always amazed that people come out to hear a physicist talk. You don't. My wife doesn't come out to hear a physicist talk, so it's amazing that you guys do. And I'm going to do just what John talked about. I'm going to briefly go through some of the evidence for God from science. I often present this evidence at universities or churches throughout the world. And then because this evidence has been so disseminated throughout the public, many scientists who don't believe in God have tried to refute the evidence. And so I've read lots of their refutations, and I want to talk a little bit about those and how I think they're inadequate to actually refute this great evidence for God from science. Before I start, though, I'm going to talk a little bit about my research. And so to show you that I'm an actual scientist, this is what the test will be on at the end. By the way, I should let you know I'm actually a professor at a university a few hundred miles north of here, whose colors are crimson and cream, who won the game that counted this year, just to let you know, okay? But, yeah, I know. We'll see what happens this year. But anyway, no, it's great to be here. I'm originally born in Fort Worth, so I have, some claim to being a Texan, even though I only lived here 5 years as a child. Anyway, I study the smallest particles in the universe. This is what we all know from the Magic School Bus. Everything is made of atoms. Atoms have at their core a nucleus. The size of the nucleus is not drawn to scale. If the nucleus was the size of this room, or if the atom was the size of this room, the nucleus would be a little pinpoint in the middle. So atoms are mostly empty space. Inside every nucleus, are neutrons and protons, and inside neutrons and protons are these particles called quarks. I've spent most of my career studying the properties of quarks, how the neutron or how the proton is put together. So how do we determine how a proton is put together? Suppose you wanted to know how your car was put together, and you didn't have any tools to take the car apart. But you want to know, how does the engine work, how does the transmission work, but there's no pliers or screwdrivers or anything to take the car apart. What would you do? Well, if you're an experimental particle physicist, you get the car going really, really fast, and you smash it against another car going really, really fast, and you watch what comes flying out. So this is what we do. Not with cars, with protons, right? Near Geneva, Switzerland is where I do my work. There's a tunnel that's 300 feet underground and 27 kilometers around, 17 miles around. I'm in the US, I forgot. All right, so anyway, and inside this tunnel, we accelerate protons to nearly the speed of light. This is a picture of inside the tunnel. These big blue things are superconducting magnets. They bend the protons. This is the tube open. One of these tubes will carry protons one way. One tube will carry protons the other way. And then in 4 different places around this 17-mile ring, we smash the protons together. This is an artist's depiction of that. Here's the tunnel. Here's one of the places we're going to smash them together. We build a big camera to see the debris that comes out when the particles smash together. And from that debris, we can understand the structure of the universe. This detector here is called ATLAS. It stands for a toroidal large apparatus, and that will be on the exam. All right, so anyway, here's the detector. These are people, just to give you some idea of the size of the detector. Protons come in this way, they come in this way, they collide in the middle, they make lots of new particles. E equals mc squared. You can actually make mass with energy, and that's what we do. And then the computer takes a picture that looks something like this. And my job as an experimental particle physicist is to understand what happened at the beginning here. These are all particles created from the collision. What happened here at the beginning when the protons smashed together. And from doing that, we understand the structure of the proton. This is one of the 2 experiments that discovered the Higgs boson in 2012. So my name is one of the 7,000 names on the 2 discovery papers. So I will claim 1/7,000th responsibility for the discovery of this particle, sometimes called the God particle, because the writer of the book about the particle wanted to sell books. So I named it the God particle. But Peter Higgs and Francois Lengoire won the Nobel Prize for predicting this particle in 1963 and 1964, and then in 2012 it was discovered. So this is what I do in my day job. In my night job, I talk about things like modern scientific evidence for God. We're not going to give proof for God. You can't prove God from science, but we can give evidence for God, and that's what we're going to do. I'm going to talk for maybe 50 minutes or so The first half of my talk will be on some of the evidence, and I'll go through this really quickly. If you've been at Reasons to Believe for a while, or you've listened to John speak or Dr. Hugh Ross, you know a lot of this evidence. And then I'm going to spend the last half of my talk talking about non-theistic responses. So theists have been saying for at least 50 years that things like this point to God. And the non-theist scientist has developed a number of arguments against these things over the last probably mostly 10 years or so. And so I'm going to address some of those things and why I think they don't refute God. And then after that, we'll give you, some time to ask questions at the very end. So let's start with the origin of the universe. 100 years ago, no one had any idea how the universe began. But since about 1929, we've made three major discoveries that give us evidence that the universe had a beginning. The first is that the universe is expanding. If the universe is expanding now, it must have started to expand. And from the rate of expansion and the stuff that's in the universe, we can infer when that starting began. And the universe started to expand about 14 billion years ago. We also can measure the amount of hydrogen and helium that's in the universe. If the universe began with a Big Bang, then our theories predict how much hydrogen and helium we should see, and what we see in the universe agrees with what we predict to about 1 part in 10,000, which is an amazingly accurate prediction. And then the third piece of evidence that has convinced scientists that the universe began with the Big Bang is the temperature. Because the universe started out very, very hot, it's like turning your oven on and getting it very hot. And then if you turn the oven off, that heat dissipates throughout the house. Well, the universe started out very hot, and even though it's been 14 billion years since then, we can still see that residual heat from the hot Big Bang. It's called the cosmic microwave background radiation. The Planck satellite and other satellites have taken pictures of that. This is the picture of the whole sky. The blue areas are slightly cooler areas in the sky, and this is the whole universe. The red is slightly warmer areas. And again, this prediction of what the temperature of the universe should look like compared to what it does agrees to 1 part in 10,000. Now, scientists don't really like the Big Bang. You will often read that scientists are looking for some way out of the Big Bang. And the reason is because if the universe had a beginning, it might have had a beginner. And that is a problem if you don't believe in the beginner. In fact, scientists will often talk in their public writings about the problem of the Big Bang. But nevertheless, these kinds of evidences have convinced scientists that the universe seemed to have a beginning about 14 billion years ago. But not only do we believe that because of what we've observed in nature, we believe that because of theoretical physics. The observational experimental physicists like myself look at the experiments and what we get through nature, while the theoretical physicists, this is a guy who was pretty smart, you've probably heard of him, the theoretical physicists will try to explain that by calculating what they think is going on. In 1915, Einstein developed his general theory of relativity, which explains how gravity works. His theory predicted that the universe would be expanding, but this was before we discovered the expansion of the universe, so he later retracted that and said, maybe my theory is wrong, maybe I need to add some factor to it, because he knew that if the universe was expanding, it might have had a beginning. In the 1970s, some physicists like Roger Penrose and George Ellis and Steve Hawking developed the general theory of relativity more inclusively, and their conclusion was that space and time actually had a beginning. So the Big Bang is not an explosion of pre-existing material. It's actually misnamed. It's the origin of the universe. It's the beginning of everything we know, space, time, matter, and energy. A more recent theory developed in 2003 by three physicists, Bourdais, Guth, and Vilenkin, basically says that any universe like ours that's expanding on average must have had a beginning. And so what we come to is this conclusion, that the Big Bang was the origin of everything in the universe: space, time, matter, and energy. Now, if you ask me, what is it like to not have space and time, I don't know. My waistline takes up more space than I would like. When I'm driving home on a crowded freeway, it takes more time than I would like. So I live in space-time. I have no idea what it's like outside of space-time. But what all the calculations and all the observations say is that the universe had a beginning of space-time. And here's the issue. If the universe had an origin, then whatever caused it, whether it's natural or supernatural, it has to be outside of the universe. If this universe had a beginning, the cause has to be transcendent. And that is why some people have a problem with the Big Bang origin. But nevertheless, all the observations, all the calculations give the same thing, that this universe had a beginning in which everything came into existence. Therefore, the cause of the universe has to be transcendent, has to be outside the universe. That's just logic. So only worldviews that include a transcendent cause are compatible with science. If your worldview does not have a transcendent cause, whether it's natural or supernatural, then you're not in agreement with what science has said. But God in the Bible is completely transcendent. Theologians have said that for a long time. Not all world religions have a truly transcendent eternal being. The Bible does. So the God of the Bible is completely compatible with everything we've understood from science. And if your idea of a divine being is not completely transcendent, that idea is incompatible with what we know from science. So I would argue that scientific observations and calculations support this idea for a biblical God. And it's not just my idea. In 1974, as the evidence for the Big Bang became persuasive, Robert Jastrow, who's an agnostic physicist, wrote this: "For the scientist who has lived by his faith in the power of reason, the story ends like a bad dream. He scaled the mountains of ignorance. He's about to conquer the highest peak. And as he pulls himself over the rock, he's greeted by a band of theologians who've been sitting there for centuries." Okay. All right, so science has discovered then what the Bible declared long ago. The correlation is amazing, that the universe had a beginning. The very first words of the Bible are that the universe had a beginning, that the stuff of the universe didn't exist at one time. The writer to the Hebrews says, "We understand that the universe was formed at God's command, so that what is seen was not made out of what was visible." We had no clue that that was true until the early 20th century. And then finally, that the Creator is not bound by space and time. Paul writes that God was active before the beginning of time. The New Testament is the only holy book in the world that explicitly describes a God who acts before time. And it wasn't until the 1970s that we knew there was such a thing as before time. Yet this writing, and in another place, Paul says the same thing, that God was acting before time. So the first piece of evidence for the God in the universe is the origin. The second is the design in the universe. This sometimes goes by the name the anthropic principle. The idea is that many of the parameters in the universe seem to be finely tuned to allow, first of all, any universe to exist, and second, life to exist in the universe. It's as if you had a control panel with 100 knobs, and these 100 knobs control things in the universe like the mass of the proton or something, and if you turn them just a little bit, either to the right or the left, you get either no universe at all or a universe that's inhospitable to life. So since we're going till noon, I can probably describe all 100 parameters. So no, I won't do that. So what I want to do is just describe a couple to give you a taste of things. So the first one I want to describe is the strength of the strong nuclear force. This is what I study in my research. Here's what's on the quiz at the end. You know everything's made of atoms. Atoms are made of nuclei. Nuclei are made of neutrons and protons. Neutrons and protons are made of quarks. By the way, does anybody know what a quark is made of? Well, maybe, but for sure. No, yeah, so strings is an option. If anybody knew, I'd like to know, because as far as I know, nobody knows, so we could win a Nobel Prize. But since none of you know, we'll keep going. All right. So the strong nuclear force is what binds quarks together in neutrons and protons and ultimately binds the nucleus together. It's because of the exact strength of the strong nuclear force that we have the periodic table. If I was to take the strong nuclear force and make it just 2% stronger, I would eliminate hydrogen from the periodic table, which would be a problem. What is H2O? Water. You'd have no water. Our sun burns hydrogen. There'd be no stars like our sun. So if I take that knob that controls the strength of the strong nuclear force and make it 2% stronger, I don't have hydrogen. I don't have a universe that's hospitable to life. If I take that knob that controls the strong nuclear force and make it 5% weaker, then the periodic table looks like this. There's only hydrogen. Now, that would make chemistry class really easy because hydrogen, right? But it's not good for life. So that's one parameter. Another parameter is the amount of matter in the universe. So the universe, as it expands, everything is attracted to everything else by gravity. If there's too little matter in the universe, it expands so fast that it can't clump together to form stars and galaxies. If there's too much matter in the universe, it's attracted so strong by gravity that it collapses almost immediately, and there's no time for the universe to exist to create stars and planets. And the amount of matter in the universe, just shortly after the Big Bang, less than 1 second after the Big Bang, was fine-tuned to 1 part in 10 to the 60th. That is, if shortly after the Big Bang, within the first half second or so, I had thrown 1 dime's worth of matter more into the universe, we wouldn't be here to talk about it. Okay? You could give me an extra dime now and it wouldn't matter, but back then it would have mattered. Now, once I gave a talk at Stanford about this principle, and a friend of mine who's a physicist came up and said, oh, you can't use the amount of matter in the universe as one of those knobs that you turn for fine-tuning. And I said, why not? He says, because we think we understand how that universe became what we call flat, how it became the exact amount of matter. It's something called cosmic inflation. And he says that because cosmic inflation produces the correct amount of matter, we can't use that as an argument that God tuned it. So it got me thinking. Suppose you have a mechanism that does exactly what you want it to do. Does that remove the need for fine-tuning? Right? So let me give you an example. Every Saturday, well, no, not every Saturday. Every other Saturday, my wife would like it every Saturday, I mow the lawn at my house, right? So every other Saturday, I got to dump gasoline in this big container into this little hole in my lawnmower. And if I try to do it, it flows all over the ground and all the lawnmowers. So I use this mechanism called a funnel. And the funnel works really well. It takes the gas, so no matter where I pour it, right into the hole. Now, does the fact that I have a mechanism that works take away for the need for fine-tuning? No, a mechanism that does exactly what it's supposed to do is itself an example of fine-tuning. And so just because we know how we get to this correct matter, it just pushes the problem back one step. You still need a finely tuned mechanism. All right. So there's about 100 of these things. Scientists make statements like this: such properties seem to run through the fabric of the natural world like a happy thread of coincidences. But there are so many odd coincidences essential to life that some explanation seems required to account for them. The last thing is the rare earth. And the idea is that the Earth seems to be a rare planet. And you have to ask the question, what's required in order to have a planet that's capable of supporting higher life forms? And by higher life forms, I mean anything more complex than bacteria. Bacteria thrives everywhere. We know of extremophiles. We'll probably find, it's likely we'll find bacteria throughout our solar system because the Earth could have seeded bacteria all over. But what does it take to support something higher, more complex than bacteria? And I won't, just for the sake of time, I'll go through this quickly. Our galaxy is a spiral galaxy. This is what the Milky Way would look like. Only spiral galaxies, which are about 10% of galaxies, can support higher life forms. And you can't be anywhere in the galaxy. If you're too near the center, there's a black hole. That's not a good place for life unless you're in the movie Interstellar. And in fact, there's too much radiation and all. And if you're too far from the center of the galaxy, there's not enough heavy elements like hydrogen and or like carbon and silicon and iron. So this is called the galactic habitable zone. And our sun happens to be right in the center. The sun is a class G star. It's the only kind of star that burns bright enough and stable enough to have a planet like the Earth that can support life. But the one thing I want to point out, because I'm going to come back to it later, is it's a third generation star. So what does that mean? If you watch the movie Contact or you read skeptics, they say the universe is big. If God cares about humans, if there's a God, why would he make such a gigantic universe and care about one little planet like the Earth? And here's my answer to that. If you start with a Big Bang and you want to create one little planet like the Earth, here's what you have to do. You have to first have the first generation of stars. Those stars are made only of helium and hydrogen because that's all that's there. When stars die, they create the other elements of the periodic table. As a star dies, it creates carbon and silicon and oxygen and nitrogen, all the things we need. But when the first generation of stars died, they didn't create enough of those things for a planet like the Earth. So the debris left over from the death of the first generation of stars eventually coalesces into the second generation of stars. Some second generation stars live not very long. They die. They produce more heavy elements. And out of the debris from them comes the third generation of stars. So if you want to, and that's what the sun is. So all the carbon in your body was actually made from burned out stars. So if you want to be poetic, you're stardust. You're made of stardust. Okay? But if you want to create a planet like the Earth, and you want to use the Big Bang to do it, it takes 3 generations of stars. That's the quickest you can do it. And 3 generations of stars takes about 10 billion years. That's when our star was formed, about 9 billion years after the Big Bang. So as the universe gets older, it gets bigger. It expands. So follow the argument. You want to create a planet like the Earth, you start with the Big Bang. The shortest amount of time it takes to create that planet is 9 billion years. And in 9 billion years, the universe gets to be 9 billion light years apart, or actually bigger. So because this is the shortest amount of time it takes to create a planet like the Earth, it's also the smallest universe you could have and create a planet like the Earth. Because the older the universe, the bigger it gets. The question isn't why is the universe so big if God cares about the Earth. The question is why is the universe so small? Because this seems to be the smallest universe you could have and create a single planet like the Earth. Anyway, there's our planet. It's got many things about it that make it suitable for life, including tectonic activity. I used to live in California. We know the results of tectonic activity there, but yet tectonic activity is actually required. Everything from its size, its rotational rate, the amount of water, its magnetic field, you go on and on for these things that are important for the Earth. The Moon and Jupiter play a role. I won't go through all this. But Peter Ward and Donald Brownlee, 2 University of Washington professors, write this: if some godlike being could be given the opportunity to plan a sequence of events with the express purpose of duplicating our Garden of Eden, that power would face a formidable task. It is unlikely that Earth could ever be truly duplicated. So all these things I'm talking about, the Big Bang, the fine-tuning, the rare earth, are things that scientists know, and they are amazed by it. If you read their popular writings, they say things like this: a common sense interpretation of the facts. I like that. That sounds like a scientist. A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. And Fred Hoyle is no theist at all. He, in fact, really struggled with the Big Bang because, in fact, he invented alternate theories to the Big Bang because it pointed to the God of the Bible. Alan Sandage was an atheist. He became a Christian because of this kind of evidence. He said, I find it quite improbable that such order came out of chaos. There has to be some organizing principle. God to me is a mystery, but is the explanation for the miracle of existence, why there is something instead of nothing. One of the most remarkable stories about how powerful this evidence is the story of Anthony Flew. Anthony Flew was one of the leading proponents of atheism throughout the 20th century. And at the age of 81, he changed his mind and became a deist, someone who believes there is a God. And in an interview in this magazine, he says, I think the most impressive arguments for God's existence are those that are supported by recent scientific discoveries. The interviewer said, so you like arguments such as those that proceed from Big Bang cosmology and fine-tuning? And Flew said yes. Right? Can you imagine spending your whole life devoted to one worldview, atheism, being a leading proponent of that, and at the age of 81, admitting that your whole life you've been wrong? Right? That takes a lot of guts. But it must mean that the evidence is extremely powerful. All right, so here's what I've said, a review for the exam, okay? The Big Bang origin says the universe had a transcendent origin. The anthropic principle said the universe appears to be designed for humans. And the rare earth hypothesis says that the habitable earth seems rare, if not unique. This is the dates that the scientific evidence began to be developed for each of these principles. There's still more evidence that comes in every day. But this is kind of old, you know. If you follow science, science happens fast, quick. 1990 is really old. So the question is, although the evidence supporting these ideas has become stronger, are there other papers and books that refute them? And over the last 15 years or so, there's been a lot of books written by non-theists in an attempt to refute this. And that's what I'll talk about in the last half of the talk. Here's some of the books. I probably read as many books by people who disagree with me, by these authors who are trying to refute what I believe, as those who agree with me. That's how I understand what is true, and that's how I understand what the best arguments for these kinds of ideas are. Stephen Hawking wrote A Brief History of Time. Larry Krauss wrote A Universe from Nothing. Victor Stinger wrote The Fallacy of Fine-Tuning, and you can see how even the titles try to refute these ideas. One of the first books I read that was really a refutation of these was The Grand Design by Stephen Hawking and Leonard Mlodinow. And when you read the first chapter, 3 questions are posed. And these are the 3 questions. Why is there something rather than nothing? Why do we exist? And why this particular set of laws and not some other? And in reading the first chapter, it became clear to me that Stephen Hawking has heard my talks, all right? Because these 3 questions exactly address the 3 pieces of evidence I just gave. Why is there something rather than nothing? That's the origin of the universe. Why do we exist? It's at least in part because of the planet. And why this particular set of laws and not some other is the anthropic principle. And what I realize is that the authors felt compelled to address these things. Why? Because they're so prevalent, they're so relevant, and they're so compelling. These arguments are so strong that atheists change their mind, and other atheists have to refute them in a popular book because of their power. Right? So let me just briefly explain the response that you currently hear to these 3 pieces of evidence I gave. The rare earth, the anthropic principle, and the origin. And I'm going to try to represent what an atheist would say accurately and then tell you why I think there are problems with it. So what's the response to the rare earth hypothesis? There's really just one, that there are lots of planets, so there must be one that's suitable for life. There are probably a trillion planets out there at least, or something like that. We found over 3,000, the number's approaching 4,000. So surely one must be suitable for life, or a bunch must be suitable for life. So let me ask the question, should we expect to find a planet like the Earth since there are so many? What does it mean to be an Earth-like planet, and what conditions are necessary? By the way, when you read in the newspaper that scientists have found another Earth-like planet, you tend to think it's something like you would see on Star Trek, right? You go land there, they have an atmosphere that works, their skin is green instead of whatever color ours are, right? But other than that, they're pretty much like us. But when a scientist says they found an Earth-like planet, they mean one of 3 things. Either the planet is rocky and not gaseous. Well, Mercury's rocky and not gaseous. It's hardly Earth-like. Or the planet is in the zone where it might have liquid water. Well, Mars is in the zone where it might have liquid water around the star, but it's hardly Earth-like. Or that the planet is about the same size as Earth. Well, Venus is about the same size as Earth. So when you read scientists have found an Earth-like planet, don't believe it. It means one of those 3 things, and that's all it means. There was an article in the Wall Street Journal recently by an astrophysicist who actually said we need to quit calling these things Earth-like planets. We have no idea if they're Earth-like, if they satisfy one of those criteria. In fact, I've given you a few criteria that you need to create an Earth-like planet. You need to be in the right galaxy. That's a 10% probability. For those of you who like numbers, I finally have some. The star has to be the right distance from the galactic center. That's a 20% probability. Some things we're going to take an educated guess. Scientists call it a back-of-the-envelope calculation. We really don't know how many planets have tectonic activity, but none in our solar system do, so let's maybe guess 20% or something, or 5% have tectonic activity. And this is a partial list of the things that we know are required to make a truly Earth-like planet, one that can support something more complex than bacteria. Here's a more complete list, right? And this is actually an old one, because I don't want to remake this slide, all right? So as we get more evidence, I don't put it on this slide. I'm going to leave this one up here, because this one has 322 parameters that we know are necessary. And when you do a back-of-the-envelope or a rough calculation, you get the probability of finding an Earth-like planet in the visible universe. And what we can see, because we don't know how big the universe is 1 part in 10 to the minus 304th. Now, there's lots of planets. There are at least a trillion or something like that. So the probability of finding one Earth-like planet by chance, including dependencies, longevity, for those of you who care about statistics, this is correlations and all, you get 1 part in 10 to the 282. Now, scientists have a name for a number this small. Ain't gonna happen, all right? That's the official terminology. So the rebuttal to the rare earth hypothesis is really easy. It's really naive to assume that simply because there are a lot of planets, there must be a lot like the Earth. All you got to do is some simple back-of-the-envelope calculations, and you realize that that's not true. This is an unsophisticated claim. It's a naive claim that just because there's a lot, there might be more like the Earth. So let's go to the next thing. What's the response to the design and the fine-tuning? So the major response nowadays to why our universe looks like it's fine-tuned is something called a multiverse. The idea is that our universe, not our galaxy, but our universe, everything in our universe is just one of many, many universes. And that in the many other universes out there, which we will probably never have any evidence for, so is that science if you never have any evidence for it, that most of those universes are inhospitable to life, but ours happens to be the one that we got lucky in because we're here and it's hospitable to life. Now there are lots of different ways of creating multiverses, and I don't want to go into all of them, but I'll say a few things. One example is M theory or string theory, which John will tell you all about since he mentioned it, all right? And in string theory, there are about 10 to the 500 different possible universes. It doesn't mean they all exist, but you can come up with a big number. There's no evidence that these exist. So any belief is not based on observational science. It's based on theoretical calculations that say maybe there is a multiverse. John Horgan in Scientific American, this was a critique of Stephen Hawking's book, The Grand Design, said, M theory, theorists now realize, comes in an almost infinite number of versions which predict an almost infinite number of possible universes. But I love this line. Of course, a theory that predicts everything really doesn't predict anything. Right? And this is the problem with these multiverse theories. They are so flexible and that they really don't predict anything. You can't say, my theory will give this observational evidence that it's right. So my editorial comment on this is that real science is based on experimental results, not on speculation. So an appeal to multiverse is not based on observation. But let's keep playing the game. What if we were to find a multiverse? What if somehow it could interact with our universe? Does that take away the need for fine-tuning? So let's ask, so first of all, there's no evidence for it, but suppose we would discover one. How would that affect the evidence for the existence of God? Would that solve the fine-tuning problem? I actually think, well, I'll tell you my editorial comment after. So first of all, we don't know what it would mean. Until we actually, there's so many different multiverse theories that until we actually find out which one is true, I can't tell you what the ramifications would be. We only know the ramifications if we know what we're talking about, and we don't. So until we develop a mathematical theory, I can't tell you exactly how I would fit it into my worldview or whether my worldview would have to change. But what we do know is among all possible universes, there's still very, very, very few that could support life. So we still live in a unique or rare universe. It's still improbable. They still require a beginning. The BGV theorem says that any multiverse of universes still requires a beginning. So it doesn't solve that problem, but it's supposed to solve the fine-tuning problem. But here's my most interesting one to me. Before we discovered the Big Bang, if we had known the size of the universe, or still today, some people would have said, man, that's a lot of wasted space. Why is the universe so big? But now that we understand the parameters necessary to make a planet like the Earth, the universe isn't the biggest it can be, it's the smallest it can be. So suppose you're God, and I'm just speculating, and you say, you know, I think I'll create a universe, I want to create human beings, and I think I'll make string theory the underlying reality of what is required to create one planet like the Earth. Oh, but string theory means I need to create 10 to the 500 universes if I want to create one planet like the Earth. Ah, no big deal. I'm God. Let's create 10 to the 500 universes because that's the underlying principle of how the universe works, string theory. And in the creation of the one planet Earth that I care about, the way the universe is structured, the laws of physics require multiverse. No big deal. That's what I'll do. Right? So it's possible that we would discover that string theory is true, multiverses are there, and we say, yeah, but we need string theory to have a universe like ours. And string theory requires 10 to the 500 universes. And so does that reduce the fine-tuning? So the discovery of multiverse may actually strengthen the evidence for God. And then finally, how many universes would an infinite God create? We know there's at least 3. He created a universe of angelic beings before ours. He created ours, and he's going to destroy this one and make a new one. We're told he's going to make at least 3. 10 to the 500? How hard is that for an infinite God? So the multiverse doesn't threaten anything until we know what it actually is. The multiverse, in fact, if string theory is true, then if you read Hugh Ross's book, Beyond the Cosmos, you know that it actually strengthens the reality of God. It explains miracles, does lots of things. If you really want more information, I highly recommend this resource from Reasons to Believe. It's a little pamphlet by Jeff Zverink, who's, I misspelled his name, but anyway, who's an astrophysicist. Here's how it's actually spelled. And he's got this book called Who's Afraid of the Multiverse? So I'd recommend that. The other response to fine-tuning comes from people like Victor Stenger, and you can see the title of his book, The Fallacy of Fine-Tuning. And his claim is that there just is no fine-tuning. It's created by humans, it's not real. So this is another book written by two astrophysicists from Australia, Luke Barnes and Grant Lewis. Luke Barnes was here, right, a year or so ago, because he was on a book tour for this book. This is a great book. I highly recommend it. Luke Barnes is a Christian. Grant Lewis is an atheist. They're both astrophysicists, and they both believe the universe is fine-tuned. Their reason for fine-tuning is different. Luke Barnes believes in God. Grant Lewis believes in a multiverse. But the idea there is no fine-tuning is completely rebuked in this book. So here's Stenger's argument. Let's go back to Stenger. And it's really interesting. He says, if our formulation of laws of nature is to be objective, it must be point of view invariant. He calls that POVI. So this is a little technical. If you're kind of bored and this is where you can take your nap, all right? Invariance implies conserved quantities. That's something called Noether's theorem. It's a mathematical theorem. Thus, here's his point. When our models do not depend on a particular point or direction in space or a particular moment in time, right? Models shouldn't depend on where you are or when you are. Then those models must necessarily contain the quantities linear momentum, angular momentum, and energy, all of which are conserved. And so the conservation principles, here's the key line. The conservation principles are not laws built into the universe or handed down by deity to govern the behavior of matter. They are principles governing the behavior of physics. So here's his 3 points. Okay? Here's the problem. His conclusion is based on a false premise. He uses this word invariant here, and he uses this word invariant here. But this word here, in the strict technical language of physics, should not be invariance, it should be symmetry. And symmetry is not the same as invariance. So by substituting the word that means the same basically in English, invariance, he can have point 2 follow from point 1. But in physics, this word should be symmetry, which is different than invariance, and then the conclusion doesn't follow. Isn't that subtle? It's so subtle, I didn't catch it when I read the book. I had to read Luke Barnes to catch it. And Luke Barnes caught it, and I go, of course. He's substituting an English word that means the same, but in physics it means something completely different. Somebody once asked me, does Stenger know that he's doing that? I don't know what Stenger knows. He's dead, right? I can't even ask him. Okay? So here's another rebuttal. Luke Barnes, so this is a popular book, The Fallacy of Fine-Tuning. Luke Barnes writes a very technical article on the fine-tuning of the universe in which he refutes Stenger. So physicist Victor Stenger wrote a popular book. Luke Barnes wrote a technical article. And those who read them both says Barnes' case is far stronger than Stenger's. The fine-tuning is real. Here's some quotes from Barnes and Geraint Lewis's book. This reaction against fine-tuning might stem from the belief that fine-tuning is the invention of a bunch of religious believers who hijack physics to their own ends. This is not the case. The field began in physics journals and remains with physicists. You can go to the physics journals and see the articles that discuss the strength of the strong nuclear force and how it's fine-tuned. You can go to physics journals and see these articles. While there is more work to be done, physics has tended to consolidate our understanding of fine-tuning. Okay? So we've talked about the response to the rare earth hypothesis. We've talked about the response to the origin of the universe. How am I doing on time? Oh, really good. Let's talk about the response, we talked about the response to fine-tuning. Let's talk about the response to the origin of the universe. So here's the first thing to say. Nobody knows what happened in the first 10 to the minus 35 seconds after the Big Bang. And we may never know. In fact, the Big Bang is sometimes used in 2 different ways. It's sometimes used to refer to the actual origin of the universe. And when you hear that scientists refute the Big Bang, they're talking about that definition, since no one knows what happened at the actual origin. But it's sometimes used to mean from the moment we start to understand the physics and the development of the universe, which is somewhere around 10 to the minus 12 seconds after the Big Bang. So if we define the Big Bang as 10 to the minus 12 seconds after the origin, then there's no controversy about the history and development of the universe. if you read that somebody has found that the Big Bang didn't occur, and some of my Christian friends who don't believe in the Big Bang love to quote those headlines, the Big Bang didn't occur. What they're talking about is not that the universe is 14 billion years old and that we understand it was once hot and dense and that we know what it was like 10 to the minus 12 seconds after the origin. What those articles are saying is that we don't know what happened at the origin, and I think there was no beginning. Okay, so be careful when you read headlines. So here's the actual proposals against the origin of the universe. There are really two major ones. The first is that there was no actual beginning. The second was that the beginning was some purely natural event. And let's talk about both those. First, let's talk about what we do know. About 10 to the minus 32 seconds after the Big Bang, the visible universe was hot, dense, and has expanded and cooled since. This number is variable. I said 10 to the minus 12. Some will say 10 to the minus 32. I once talked to an astrophysicist, and I said, how far back are you sure that you understand the history of the universe? He would only give me a half second after the Big Bang. All right. But whatever it is, we understand 14 billion years of development. Everything we do know, all the theoretical calculations, all the observations, everything we do know points to an actual beginning, even if there's a multiverse. We also know that this thing I haven't even talked about called the entropy of the universe, which is in layman's term how orderly the universe is, was extremely low. In other words, the Big Bang wasn't a chaotic event. It was an orderly beginning. One physicist, Roger Penrose, has calculated that the entropy of the universe, how ordered the Big Bang was, how precisely fine-tuned it was, is fine-tuned to 1 part in 10 to the 10th to the 123rd power. That really ain't going to happen, okay? Sean Carroll, who's an atheistic physicist who doesn't believe in God, he is a thoughtful writer, though. I write a blog, and in one of my blog entries, he actually has like 5 models for the beginning of the universe, and he throws out 4 of them immediately because he says they don't solve the entropy problem. And then he has one that he thinks does. I don't think it does, but that's another story, all right? So here's what we know given science. Everything that's scientifically observable and measurable gives support for what I've said. A transcendent, intelligent God who cares about humanity. So if you don't believe in God, you have to appeal to the gaps in our knowledge, the things we don't know. What happened in the first 10 to the minus 32 seconds? Nobody knows. I call this an appeal to atheism of the gaps. So Christians are often accused of talking about the God of the gaps. We don't understand in ancient times how lightning occurred, so the Thor god must have done it. And then we find out lightning, is electromagnetic discharge, then we don't need God. And I think most God of the gap arguments are really poor arguments. God isn't seen in what we don't know, he's seen in what we do know. We do know that the universe had a beginning. We do know how carbon is formed in stars. We do know about inflation. All the things we do know look fine-tuned. But the atheists can't point to the things we do know because they all look like there's a beginning and a designer and someone who cares about humanity. So the atheist has to go to the things we don't know, the first 10 to the minus 32 seconds, and say, well, maybe I can find something there that precludes God, the atheism of the gaps. All of these proposals are speculative, like the multiverse. They all require, get this, some new unknown physics to actually supersede what we do know. Okay? Now that's possible. That's happened in the past, where we've discovered some unknown law of physics that supersedes what we do know. But that's what you're counting on if you try to remove God from the plain sense of what we do know. Okay? Almost all the proposals contradict the BGB theorem. It's hard to get around that, and very few solve the entropy problem. But let's talk about them anyway. The first one is that there's no actual beginning. So oscillating universes do this. Oscillating universes still require a beginning. Multiverses still require a beginning. Stephen Hawking's no boundary condition is one that he claims doesn't require a beginning. I would claim it does. Here's the difference. It's a little bit technical, so I'll try to explain it. So general relativity says the universe had what we call a singularity. It's a point of infinity. I kind of liken it to an ice cream cone with a sharp point. Okay, that point comes down to a point where it just stops. It's infinite. But if you have an ice cream cone with a rounded point at the bottom, that doesn't have that sharp point. It doesn't have a singularity. But it still has a beginning, right? It has a point where the curvature quits going like this and goes like this. You can walk north till you reach the North Pole and start to walk south, even though there's no sharp point where you stop and turn the other way. So just because Stephen Hawking has a no boundary condition, which has a smooth bottom instead of a sharp bottom, you don't lose the beginning. So when I read his book, A Brief History of Time, it astonished me that that's his way to get around the beginning. He's removed what we call a singularity, but he hasn't removed an inflection point where you actually have a beginning. This is a great one because this one made the national or international news. These two guys, Ali and Das, developed what they called an idea for the beginning, and it says there is no beginning. So it's a little technical. They use something called Bohmian quantum trajectories. So if I want a beginning, I have to have that point where everything comes together, whether it's sharp or smooth. Well, Bohmian quantum trajectories, by definition, cannot come together. Okay, so their presupposition is the lines can never come together. They do the calculations, and guess what? They don't come together. Therefore, there's no beginning. Right? And this made international news that there is no beginning of the universe. But when you read the paper, it's because their presupposition is that there can't be a beginning. And so their conclusion is there can't be a beginning. Right? And if you read the headlines and if you don't understand the science, you go, oh, maybe there's no beginning. Okay? Here's what Alexander Vilenkin, one of the authors of the BGV theorem, says. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem, right? It's the problem of a cosmic beginning. The second possibility is that the beginning of our universe was purely a natural event. And there's lots of postulates. The universe is eternal but stagnant. The universe is one in a series of universes that bounce. The universe is a result of some kind of quantum fluctuation. So let's briefly go through some of these. The universe is eternal has real problems. It still requires infinite fine-tuning in the past. It's not stable, so it can't exist eternally. When you do the math, you find that it decays, quote, decays to a real universe very quickly. So it really has lots of fatal flaws. I'm just going through these because you may have read about these if you're a science nerd like me in the popular press or something. The universe is one in a series of universes. There's lots of different models. None of them solve the entropy problem. None of them solve the BGV theorem problem. Let's just leave it at that. The universe is a result of some kind of quantum fluctuation. This is the one most people will go to. In fact, if you Google the Big Bang and you look at images of the Big Bang, lots of them at the very beginning, where everything comes together, where the universe starts, actually write quantum fluctuation. So this is the one that most people hold to. The problem is there are such things as quantum fluctuations that create particles, but they're only within the space-time fabric of our universe. So you're not creating a universe from nothing, as Larry Krauss suggests. You're creating a universe from something that allows universes to pop into existence, which is not nothing. No philosopher, no scientist I know personally would agree that Larry Krauss's nothing is truly nothing. The only people I know that agree it's nothing are Larry Krauss himself and Richard Dawkins, who already thinks there is no God, right, and is pretty adamant about it. So this is not a fluctuation from nothing. It's a universe from some pre-existing entity that's transcendent from our universe, which I say sounds a lot like God. Right? So in saying the universe came from nothing, it's not nothing. It's from something outside the universe that we don't understand that has the capability of creating universes. Yeah. So again, as I said before, I'm being redundant because I want you to pass the test. All right, none of the above proposed models have any observational theoretical evidence. All the models require some laws of physics to exist before the universe began. But there's even a more interesting question, and again, Vilenkin brings this up. The description of the creation of the universe from nothing is given in terms of the laws of physics. That makes you wonder, where are these laws? If the laws describe the creation of the universe, that suggests they existed prior to the universe. The question that nobody has any idea how to address is where these laws came from and why these laws in particular. Nobody? I have some idea of where the laws came from and why these particular laws in particular, right? But he points to the same fact that Stephen Hawking writes in A Brief History of Time. Equations describe the universe. They don't cause anything. If I have a model of this building by an engineer, it tells you how the building is going to be put together. It describes the structural forces and how we're going to make sure it stands, when the tectonic activity occurs or whatever. But it doesn't build the building. The equations are descriptive. They're not prescriptive. They don't bring anything about. Why these laws? But he doesn't even say, and why do the laws create anything? Right? But there's one more thing. So from the biblical point of view, so I once did a study on how should I see God in nature from the Bible. And the first answer is, well, God does miracles. He violates the laws of nature. But that's not the primary way the Bible says we should see God in nature. The primary way the Bible says we should see God in nature is the fact that nature works so well. One of the most famous verses on seeing God in nature is Psalm 19:1. The heavens declare the glory of God, and the skies proclaim the work of his hands. But nobody reads Psalm 19:2 and 3 and 4. They tell you how the heavens declare the glory of God and how the skies proclaim his name. And what does it say? The sun rises like it's supposed to. It gives heat to everyone. It goes away when it's supposed to. It finds a tent at night to hide. It works. The sun works for everyone. It's really cool. That's how you see God's nature. The Bible says God feeds the lions. Ancient people knew how the lions were fed. They hunt. It's not saying that God is seen because he supernaturally throws raw meat from heaven. It says God is seen because he's made the lions hunt. He feeds them. It's an active tense. He clothes the lilies. Oh, I tell my Baptist friends, he makes wine. That's a good one, right? That's what it says in the Old Testament. God makes wine. And these are all natural processes. And so this is how you see God in nature. Suppose someday we discovered that the universe was some kind of quantum fluctuation. Does that remove God? No, it tells me how God brought the universe into existence. What does Genesis 1:1 say? In the beginning, God created this universe. Does it tell you how he did it? Does it tell you whether or not there was a pre-existing universe? Does it tell you whether or not he used a quantum fluctuation? So what I would say is the first statement of the Bible is proven. This universe, space-time, matter, and energy, had a beginning. If we find somehow a natural reason for this universe, which I doubt we will, but let's say we do, all it says is it tells me the mechanism, just like inflation tells me the mechanism. The first verse of the Bible has been basically proven beyond a reasonable doubt by what science has discovered, regardless of how God did it. So here's the almost conclusion. 100 years ago, there was no evidence about the origin of our universe. Everything since then has said the universe has a beginning. Everything we know, all scientific evidence. The fine-tuning of our universe has been developed. It's supported by known physics. Attempts to refute it seem pretty inadequate. So the non-theist has to appeal to things we don't know. So consequently, this is my concluding statement. The proposal that a transcendent, intelligent being created and designs the universe is arguably, I would say, the best explanation given the scientific evidence. All right, so that's a short, brief, fast talk about lots of things. As John said, I have details. About 2 years ago, one of the people in my Reasons to Believe chapter at Norman, Oklahoma said, would you please get an online presence because nobody knows you unless you're on social media. So I started a blog, a YouTube channel, all the stuff you're supposed to have. So if you want more information, and it's all written, I always try to write a level, somewhat like this talk, although the last part was a little technical, but where you can understand it, where you can say to someone who's non-technical, here's why I believe the Big Bang points to God. So there's some resources.